So thank you very much for the introduction, and thank you for the invitation. So what I present today is joint work with David Conlon and my advisor, Jacob Fox, and it will be on several questions around subset sum. So in additive number theory, there are a number of questions about representability of certain numbers as the sums of elements from a particular sequence or a set. And when you don't have a constraint on how many terms in a sequence you are allowed to use, those questions can be rephrased in terms of the set of subset sums. So let me now define the main object of the talk as a set of subset sums. And for a set A of numbers, it can be a subset of the natural numbers, say. The set of subset sums, which we denote by sigma of A, is the set of all numbers that can be represented as a sum of finitely many distinct elements of A. And so, in other words, it's just the collection of all sums of finite subsets of A. And when A is a sequence of numbers, we also overload the notation, and we denote by sigma of A the set of sums of the set of numbers that can be represented as a sum of distinct terms of the sequence A. So the first set of questions that we will look at will be about whether we can represent all sufficiently large positive integers as a sum of a certain set or sequence of numbers. And those will be about completeness of sequences. And given a sequence A of natural numbers, we say that that sequence is complete if sigma of A contains every sufficiently large positive integer. And in other words, every sufficiently large positive integers can be written as a sum of distinct elements of A. And we say that A is entirely complete if this property holds for every single positive integer. And those two notions are in fact probably very familiar to us already, because this is one classical example. The sequence of all powers of 2 is entirely complete. In fact, it satisfies a stronger property that every positive integer can have a unique representation as a sum of distinct powers of 2. However, if we remove any single term from the sequence of powers of 2, then we immediately lose the ability to represent infinitely many positive integers. There are also other examples. So Sprague proved that the sequence of perfect powers I to the k is a complete sequence. And a result of Birch shows that if you take the set of all numbers of the form p to the I times q to the j, where p and q are two fixed co-prime integers, then this sequence is also complete. So complete sequences are, so next I will give a complete characterization of entirely complete sequence. So in a sense, if we want to know if a given sequence A is entirely complete or not, it's very simple. It's entirely complete if and only if the following condition holds. So the first term of the sequence has to be 1. And then for every later term in the sequence, the kth term must be at most 1 more than the sum of all previous terms of the sequence. So let me give a very quick proof sketch of this. So in one direction, if there is any one term of the sequence AK, where AK is bigger than this number over here, then we can check that this number cannot be represented as a sum of distinct elements of the sequence, right? Because if we use, in that sum representation, we use a term with index at least k, then that sum will be already bigger than this number. And if we are not allowed to use any term that's with index at least k, then the largest number we can represent is this sum here, and this one is larger than that. In the other direction, we can use induction to show that once this condition is satisfied, then the set of subset sums of the first k terms in the sequence always contains the interval from 1 to the sum of the first k terms in the sequence. And this is very simple, but it's also a useful idea that we will encounter several times more later in the talk. So let me quickly go over it. So if by induction we suppose that the set of sums of the first k minus 1 term contains the interval from 1 to the sum of all these terms, then once we allow also to add the element ak, we will simply get all of these previous sums and also those sums shifted by ak. Right, so this is ak plus 1, and to AK plus the sum of these AJ. And you can now just quickly check that once this condition is satisfied, then the old sum and the shifted one will simply, we can simply take a union, and that will be this longer interval here. Okay, so in some sense, entire completeness is a simple property to verify, but we'll be interested in a different notion, it's a robust notion of completeness. As we saw previously, if we take a complete sequence, for example, the sequence of powers of 2, it can be quite sparse in the sense that there are only about log n terms of the sequence that are smaller than n. However, it's very fragile in the sense that if we remove any one term, then it will immediately lose its ability to represent large positive integers. So we want a robust notion of that. And the notion we will talk about is the notion of Rmc completeness. And a sequence is Rmc complete if for any R coloring of the sequence, or in other words, for any partition of the sequence into R parts, every sufficiently large positive integer can be represented as a monochromatic subset sum. Or in other words, this union of the subset sums of all the color classes will contain all sufficiently large positive integers. And as before, we say that a sequence is entirely Rmc complete if this property not only holds for sufficiently large integers, but for all positive integers. And there's one quick remark I want to give, in that we cannot generally ask for one color class AI. We cannot ask that there exists a color class AI with a property that sigma of AI contains all sufficiently large positive integers. Because even if we take the sequence A to contain all of the positive integers, then we can still construct two colorings where each color class will miss arbitrarily large positive integers. However, the union of the subset sum of the two color classes will cover all positive integers. And so the coloring is easy to construct. We simply alternate between the two colors, and we give them increasingly longer intervals. And if we space out those intervals enough, then we can check that there will be arbitrarily large integers that cannot be represented as a sum in either color, that each color will miss arbitrarily large positive integers as a sum. So so the notion of Rmc completeness goes back to Burr and Erdős, and they showed two results there. First, they show that there is a sparse entirely 2-Ramsey complete sequence. So there's a 2-Ramsey complete sequence with the property that there are only about log n cubed many terms of the sequence which are smaller than n. And they also show a lower bound on how sparse 2-Ramsey complete sequence could be. So they show that if there is a sequence A, if any sequence A satisfies that there are only log square of n roughly many terms in A that are smaller than n, then A cannot be 2-Ramsey complete. And their construction here is an explicit construction by working with by playing around with powers of 2, and it doesn't generalize to more than 2 colors. So in the paper, they pose 2 questions. The first question is to improve those bounds to see what's the right order. And the second question is to extend to the R color case. And Erdős later reiterated those 2 questions, and he even offered prize money for those. And so in our paper, we completely resolved the 2 questions. So first, we show that for any number of colors R, at least 2, there is an Rmc complete sequence A, for which there are the intersection of A and the first n integers has size at both a constant, an absolute constant, times R times log square of n. So this matches for the case of R equals to 2, this matches the behavior of the lower bound by Burr and Erdős. But yeah, and we also show that this is actually tied up to an absolute constant in the sense that for any sequence A such that there are only a little constant times R times log n squared many terms up to n, then that sequence A cannot be Rmc complete. So we characterize also the dependency on R in the bound. So are there any questions about the result? Okay, so And so we see that once we move to 2-Rmc complete, we already must have a different growth rate compared to if we just ask for a complete sequence, like the sequence, the powers of 2s, we only need log n term to in the sequence. But here we have to move to log n squared, and that's tight. So next I will give a sketch of proof of this and introduce our framework for studying subset sums, and that will also be connecting to the later results that I present in the talk. So the main lemma behind the proof of this theorem is this lemma, and it roughly says that for all x sufficiently large, if we look at the dyadic interval from x to 2x, then we can pick a subset A of roughly a constant times epsilon inverse times log x many elements. So here epsilon greater than 0 is an arbitrary parameter. So for any epsilon greater than 0, then if x is sufficiently large, this property holds. And the set A should have the property that if we take any subset A prime of A that has size at least an epsilon fraction of A, then the subset sums of A prime will contain a particular long interval. This interval has length on the order of x log x. And from this lemma to the theorem is quite simple. So for each, we will take epsilon to be equal to 1 over r. And then for each sufficiently large j, we look at the dyadic interval from 2 to the j to 2 to the j plus 1. And then we take a set aj that has the property given by this lemma in that dyadic interval. So if we take our sequence A now to be just the union of those sets aj, let's look at an R coloring of aj. If we have an R coloring of aj, then some color class must occupy at least a 1 over r fraction of the set aj. And since we choose epsilon to be equal to 1 over r, that means that there is one color class of aj for which the subset sum contains the long interval here. And that's the interval from yj to 3yj for yj equal to this value. And now you can just check that if we have this property for all j sufficiently large, then those intervals will simply chain up to cover all sufficiently large positive integers. So we have every large positive integer as a monochromatic subset sum. So everything boils down to the proof of this lemma. And I will do one further step of reduction in that we only need to first show that a certain subset of A prime has in the set of subset sum interval of length at least 2x, and then we will bootstrap this interval to the one with length on the order of like x log x. So this is the statement of the main lemma. Well, first I should tell you how we can choose the set A. And the first idea is to choose A randomly. However, we can see that this could not work, because if we choose a set A randomly from a dyadic interval, it's very likely there will be about half of the elements of A that are even. And if we take A prime to be the even elements in A, then there's no hope that the set of subset sums of A prime will contain an interval. They can only contain even integers. So we'll have to change this idea slightly, and perhaps the visibility issues are the only obstruction here. So what we could try is to choose A randomly from only the integers in x to 2x with no small prime factor. And then we can indeed check that this works. So our choice of A is a sequence of C epsilon inverse log x, many elements of x to log x, of x to 2x, with no small prime factor, with no prime factor at most log x over 2. And we choose those elements uniformly and independently at random. Now, after that, we will show that if we choose A randomly that way, then this property is satisfied with high probability. And in fact, what we will do is to simply fix a subset I prime of epsilon A many indices of the interval from 1 to C epsilon inverse log x. And once we fix these indices, we have also fixed a subset A prime of A. So we look at the subset of A corresponding to the elements with those indices. And we'll show that the subset A prime will satisfy the last conclusion here with very high probability. And this probability will be so close to 1 that a simple union bound over all choices of subsets of A will show that the property here will then be satisfied for all subsets of A. So next, we will focus just on studying this subset A prime of A, which also, once we fix the indices, it will just contain uniformly and independently chosen elements. Right? So after these steps, we have reduced to the following goal or lemma. And in this goal, we choose out a sequence A prime of uniformly and independently elements with no small prime factors. And we want to show the existence of a long interval in the set of subset sum. This is one further reduction. So we'll fix one arbitrary subset A1 prime of A prime of an appropriate size. And then there's a remaining part, which is A2 prime. And then we'll show that sigma of A1 prime with very high probability will contain an interval of length 2x, of length at least 2x. And then we will extend it to the interval that we need. So to extend that interval, we'll use the following lemma of Graham, but it's actually it's a very simple but also useful result. So this lemma says that if we have a set A such that sigma of A contains an interval of length y, and then we have one extra element little a, which is not contained in A, and little a is smaller than or equal to y, then once we allow to add also this element little a to the set A and look at the set of subset sum, then that will contain the longer interval, which is of length y plus a. So we extend the previous interval to one with length that is a longer. And the proof of this is kind of similar to the one we saw for entirely completeness. So if sigma of A, so let me write a useful but simple identity. So sigma of A union this extra element little a, this is simply sigma of A union A plus sigma of A. And therefore, if you have an interval from x to x plus y in sigma of A, and once you shift this interval by A, you will simply get a longer interval whose length is extended by A. Once you have this condition that A is smaller than or equal to y, which is an important condition. And because all of our elements of A prime are at most 2x, that is why we set out to find an interval of length 2x. And then we can repeatedly apply Graham's lemma to obtain the much longer interval of length x log x in sigma of A prime. So we'll choose A1 prime to be a small constant fraction of A prime as A prime over 8. And then A2 prime will be the remaining 7 over 8 fraction of the elements. And A2 prime will help to extend the interval. And A1 prime will help to create the initial interval of length 2x. So the crucial step now is to show that sigma of A1 prime contains an interval of length at least 2x. And to do this task, we'll use our general framework for finding intervals in subset sum. And this framework will be used several times in our later applications as well. So let me give a general discussion of this framework. It proceeds in 4 steps. And so we have a set A that we want to show that there's some interval contained in sigma of A. And first we partition A into L parts. And here L is usually an absolute constant that is chosen appropriately. So we partition A to L sets of roughly equal size. And then for each of the sets in the partition AI, we further partition them into 2 parts, AI prime and AI prime prime of appropriate sizes. And then we show that for any element of AI prime prime, the set of subset sums of AI prime modulo A is large. So in this step, we look at the set of subset sum modulo a fixed number little a. And in the third step, we'll use the conclusion of the second step to show that sigma of AI, which is sigma of AI prime and AI prime prime, and we'll see why we write this way, has large size, and in particular, it is dense in some interval. And in the final step, we'll use the conclusion of the third step. So now we have L sets, sigma of AI, which are all dense in some interval, and we'll now sum them up and use a result to show that once we sum dense subsets of intervals, the sum set will contain a long interval. So if we piece together on those 4 steps, we have been able to show that sigma of A contains a long interval. So the crucial step in this framework is the second step, and it has to be tailored to each application. This is usually the hardest step. And it's the step where we want to show that the set of subset sum modulo some number is large. So we'll see it how it appears in each case. So let me now just step through how we apply this framework to the situation of our main lemma, which we recall we want to create some interval of length at least 2x in a set of subset sums of some set. So we go according to the first step. We partition A1 prime to L set, and then we further partition each of them into 2 parts. Then in the second step essentially boils down to the following lemma. This lemma says that if we have a sequence of C log X elements where C is just an absolute constant that is large enough, and we choose those elements uniformly and independently at random from the set of integers in X to 2X with no small prime factor, then with very high probability, the set of subset sum sigma of S taken modulo M will be have size at least X over 4. So later we will take M to be just another element of this interval with no small prime factor. So you can just think of M as one of those elements. And we'll apply this lemma here with S being equal to AI prime prime and with each M in AI2 prime prime. And that gives us this conclusion, which is exactly the conclusion of step 2 of the general framework. And so for everything here, we can just do it for a fixed M at a time because the probability will be very close to 1. So all of the union bound will just work. Then in step 3, we use the conclusion of step 2 to show that sigma of AI prime prime is large. And we'll use the following lemma, which also has a simple proof. So this lemma says that the set of integer, if A is a set of integers and M is some integer that is not contained in A, for which sigma, the size of sigma of A modulo M is at least H, then once we allow to sum M together with A, the set of subset sum has size grow by at least H. And the reason for this is simply that if we recall sigma of A union M, this is just sigma of A and together with M plus sigma of A. And for each of the modulo M class in sigma of A, once we add M to it, it must extend by 1 extra element. And so if there are at least H modulo M class in sigma of A, once we add the element M, we'll have to extend by at least H extra element, which explains for this bound. Okay, so after that, we can come to the final step, which is just to sum together the sigma of AI prime prime. There are L of those, all of which have large size, and we can easily find an interval so that sigma of AI prime prime is dense in that interval. And we'll invoke the following result of left to show that the sum set of those L sets must contain a long interval. And roughly, the result of left shows that the sum set of 2 over P sets of density P in an interval I, with a condition that none of them are contained in a non-trivial arithmetic progression. So they cannot be all multiples of some fixed number, for example, have to contain an interval of length roughly 2i. And here for us, P will be an absolute constant. And so left result comes with a tight constant here, and it's tight in several senses, but for our application, that will not be very crucial. So we can just use much weaker results where the constants are not tight. And in fact, for those, we can also use a version of our framework to deduce a weaker version of left results. But once we have this, we have completed the 4 steps of the framework. And once you go through that, you can find indeed an interval of length at least 2x in sigma of A prime of A1 prime. And the only missing step here is the proof of this key lemma. That's the main content of step 2. And this is the most non-trivial part of the argument. So I will only now give a very proof sketch for this step, proof of the key lemma. And the very rough idea is this: if we consider the partial sum, so sigma sub I, which is a set of subset sums of the first I random elements of the sequence S, and we take its modulo M, then we can try to show that once we include each extra random element Si plus 1, this set of partial sum will grow by a large amount, will grow significantly. And in order to show that each element, the random element Si plus 1 likely grows the size of sigma I significantly, that essentially boils down to showing that the set of elements X, for which once we add X, the set of subset sums sigma I doesn't grow significantly, is small. So we call those elements X the almost period. So if the set of almost periods is small, then with high probability, the random element Si plus 1 will not be one of those. And to show that the set of almost period is small, we use some double counting argument, and we use the stability of the set of almost periods under iterated sum set, and use some sum set style there. So essentially, we have been able to reduce the original question on subset sums of some of distinct elements to analyzing the set of almost periods, where the operations involved are iterated sum sets and operations that are more amenable to classical tools in additive combinatorics. Okay, I won't be able to say much to give more details of the proof of the key lemma, but if there are any questions about any part of the proof, I'll be able to take them now. Okay. Otherwise, I'll discuss a little bit about some extensions of the previous result. So we can also ask if we restrict to a subsequence of the sequence of perfect powers I to the k, or let's say we just restrict to a subsequence of the sequence of polynomials value Tm for a fixed polynomial P, if they're a complete or if they're a sparse Ramsey complete sequence. And that will be next what we study next. And to do this, let me first slightly generalize the notion of completeness to a sequence of real numbers, and it is an obvious generalization. So a sequence A of real numbers will say to be complete if sigma of A contains all sufficiently large positive integers, just as before. And so the first question is, for which polynomial P do we have that the sequence Tm, where we plug in all m being all natural numbers, is a complete sequence? And this is completely characterized by a previous result of Graham. And there was also a different analytic proof before that by Castle and a previous result of Ross and Securet. And Graham gives so we know a complete characterization of what polynomial P is complete. And if so, the characterization is that if we write P in this form, then P is complete if and only if the highest degree coefficient alpha k is positive, and then all of the coefficients are rational numbers. And if we write them in reduced form, the greatest common divisors of all the numerators is equal to 1. So there's a simple characterization of complete polynomials. Next, we'll move to the notion of Ramsey completeness. So we want to ask for subsequences of polynomial value sequence that are Rmc complete. And this was actually a question of Burr and Erdős in their paper. So they asked which polynomial sequences are Rmc complete. And we show that for any complete polynomial P, that polynomial sequence is also Rmc complete for any number of colors R. And in fact, we show something stronger. We show that for any complete polynomial P, so the sequence, as long as the sequence Pm is complete, then we can take a subsequence of the polynomial values Pm so that it's sparse in the sense that there are only log n squared times R times a constant depending on P many terms in the sequence that are smaller than n, and the sequence is Rmc complete. So essentially we have subsequences of polynomial sequence that are as sparse as it can be and also Rmc complete. And so the proof of this also roughly follow along the lines of the previous result, although it's a bit more complicated because we have to deal with the polynomial values. And We also consider a density analog of the previous notion of completeness. So our previous notion of completeness is about what happens when we R partition or R color the sequence A. There's a natural analog of that to be considered what if we take out an epsilon fraction of the sequence A. So we say that the sequence A is epsilon complete if every subsequence A prime of A, for which A prime takes up an epsilon fraction of A up to any interval from 1 to n for all n sufficiently large. So A is epsilon complete if every subsequence A prime of A taken out this way is complete. And one caveat here is that the notion of density completeness is not monotone with respect to the sequence A, in the sense that if we take a sequence A and we add more elements and the original sequence is Rmc complete, then once we add element, it's still Rmc complete. But if we have an epsilon complete sequence and we add more elements, it may not be epsilon complete anymore. So an example of that is if we take all the positive integers to be the sequence A, then it's not even 1/2 minus delta complete for any delta bigger than 0, because we can just take the sequence A prime to contain all of the even elements of the sequence A. And however, we can indeed show that there exists epsilon complete sequence. So we can use the result of Szemerédi and Vu to show that if we take a subsequence A of the prime numbers with at least a constant times square root n many terms up to n, then the sequence A is epsilon complete. And so the question for us is how sparse can an epsilon complete sequence be? And we give a complete characterization of that. So there's a naturally defined sequence of numbers Fi that characterize the growth rate of epsilon complete sequences. So any epsilon complete sequence A must be growing slower than the sequence Fi. And also there exists an epsilon complete sequence A which grows on the same order as Fi. And then we can work out how fast Fi grows, and that gives the following corollary. So any epsilon complete sequence A must have that in the first n integers, there are at most roughly 2 to the square root of log n many terms in the sequence A. And this is also essentially best possible. So those are all the results around completeness that I want to talk about. So far we have been focusing on asking whether we can represent all sufficiently large positive integers or all positive integers as a sum of a certain sequence or a set. In the next part of the talk, we will turn our attention to focus on whether we can represent a fix or an arbitrary positive integer, a fixed in positive integer as a sum of distinct elements of a sequence or a set. So the first question we consider here is a problem of Erdős. So he asked to estimate f of n, which is the minimum number of colors R, for which there is an R coloring of the positive integers less than n, so that n cannot be written as a monochromatic subset sum. So we want to color only elements from 1 to n minus 1, and we want to avoid n as a monochromatic subset sum. And the question is, how many colors do we need? So as a simple example, we can look at f of 23, and we can try a greedy coloring. So we just put all of the first few elements in red, and we cannot put 7 in, because once we put in 7, then we can sum the red elements and represent 23. So the first color class consists of the first 6 numbers, and then we continue this in this greedy way. And the second color class will be 7 to 11. And then the final color class, well, we can take just all the remaining elements between 12 and 22. So you can easily check that if you sum any 2 elements from here, the sum will be already at least 24, and therefore we avoid 23 as a subset sum. In particular, that shows that f of 23 is at most 3, because we can use 3 colors to color 1 to 22, and we avoid 23 as a monochromatic sum. And in general, we can generalize this greedy coloring, and we can see that we can use about square root n over 2 colors and avoid n as a monochromatic sum. However, we can generally do better. So Alon and Erdős in 1995 shows an upper bound on f of n that it grows at most roughly on the order of n to the 1/3 divided by log n to the 1/3. And this is an extra factor of log n to the 1/3. And in the same paper, they actually show a lower bound on f of n of the order c times n to the 1/3 over log n to the 4/3. And this result, this lower bound on f of n was later improved by Vu using his seminal result with Szemerédi. And that using that result, the power on log n is improved from 4/3 to 1. So n to the 1/3 over log n. So we know that if we use at most a little constant times n to the 1/3 over log n many colors, then n can always be represented as a monochromatic sum. And if we have this many colors, then we can avoid n as a monochromatic sum. So the Alon and Erdős suggest that perhaps this upper bound is closer to the truth. And we indeed show that that is the case. But furthermore, we determine f of n up to an absolute constant for all n. So for all n, f of n up to an absolute constant is given by the following function. So first we see that it's the power of n to the 1/3, and the power of log n is indeed log n to the 1/3, as in the upper bound by Alon and Erdős. But the log n correction factor is a little bit different. So what we have is n over phi of n, where here phi of n is the Euler-Toten function dividing by log n to the 2/3. And so n over phi of n is always between 1 and roughly order log n. So if n over phi of n is as large as it could be, that's around log n, then we actually recover the upper bound of Alon and Erdős. That's n to the 1/3 times log n to the 1/3 over log n to the 1/3. So that upper bound is tight whenever phi of n achieves essentially its maximum value. So when n has many small prime factors. But when n doesn't have many small prime factors, it is not tight by some fluctuation of order log n. So we also see that f of n is not monotone. It has multiplicative fluctuation on the order of log n. So in the next part, I will give a sketch of how we determine f of n, and it will come in two parts. There's an upper bound on f of n, and the upper bound is essentially a construction of a coloring that avoids n as a monochromatic subset sum. And then there's a lower bound, which we have to show that when there are few enough colors, then we can always represent n as a monochromatic sum. So the lower bound is much harder. And I will first talk about the upper bound, which is construction of the coloring, and show how we improve over the original Alon and Erdős construction. So if we rephrase, then the upper bound in the Alon and Erdős result goes as follows. So if we have n r, the number of colors r is a big constant times this quantity, then there is an r coloring of the interval from 1 to n minus 1, which avoids n as a monochromatic sum. And the coloring proceeds in three types of color. And the first type of color, we will color all of the large elements. And essentially, we color all of the elements from n over r over 2 up to n and up to n minus 1. And we'll simply do it by using those harmonic intervals. So we first color all the elements from n over 2 to n minus 1 with one color. And then we color all of the elements from n over 3 to n over 2 with one color. So if we look at each of those color classes, we can see that they cannot sum to n. For example, if we use j terms, then the sum will be less than n. But if we use j plus 1 terms, then the sum will be bigger than n. So all of those color classes avoid n as a monochromatic sum. And we use r over 2 colors to cover the large element. And that allows us to cover all the integers from n over r over 2, roughly n to n over r to n minus 1. So now we have the remaining integers from 1 to 2n over r that we have to color. And we'll use our second type of color classes. And this will avoid n by a different reason, by divisibility reason. So for each of the first r over 4 primes p, for which p is not a divisor of n, we'll color all the multiples of p with one color. Again, now trivially, each color class must avoid n as a subset sum, because any sum of the multiples of p will be a multiple of p, and we choose p to be not a divisor of n. So any sum will not be equal to n. And Now, after we use type 1 and type 2 colors, we have very few elements left. They are essentially prime or prime-like integers, and there are very few of those. So in the third type of color class, we just simply group all of the remaining uncolored integers and partition them into at most our 4 color classes, so that in each color class, the sum of all elements is less than n. And so trivially, we also avoid n as a monochromatic sum in those color classes. So if we want to go through the calculation, one can check that with these 3 types of color classes, we can use this many colors and avoid n as a monochromatic sum. So for our improved coloring, which we call improved with a factor of n over phi of n, so we have to use the divisibility or the prime divisors of n to improve over the previous construction. The first 2 steps will be essentially the same as the construction of Alon and Erdős. So the first 2 types of color the first type will cover all of the large elements, and the second type will still use all the multiples of primes p that are not divisors of n. But after that, we'll not group the remaining elements arbitrarily. And essentially, what we will take advantage of is that the fact that the primes are not equidistributed modulo d, especially if we choose d to have many small prime factors, because primes have to be co-prime to d. So for the third type of color classes, we'll choose some d so that d is co-prime to n, d is large, and phi of d is small. And now, once we have fixed such a d, for each t that is co-prime to d, we'll let xt be one integer from 1 to d with the property that xt is concurrent to t inverse times n modulo d. And for each such t, we consider 2 color classes. The first color class consists of those a concurrent to t mod d with a having size at least n over xt. And the second color class will be those a concurrent to t mod d and a lies in this interval from n over xt plus d to n over xt. And so here for each t co-prime to d, we have 2 color classes. So in type 3, we have 2 times phi of d many color classes. So why do we avoid n as a monochromatic sum in those color classes? We'll use this observation. So if we have a sum of s elements that is equal to n, and each of the element is concurrent to t modulo d, then we can conclude that s must be concurrent to xt modulo d. So in particular, let's look at this color class. This color class contains all of its elements are concurrent to t mod d, and they have size at least n over xt. If we apply this, we see that, okay, if we have a sum of elements in that color class, which is equal to n, then we must use either xt term or xt plus d or more terms. And if we use xt terms, then we already exist n. So we cannot represent n as a sum of that color class. And by a similar reasoning, we can see that n is not a subset sum of elements in this color class. Okay, so the type 3 color classes also avoid n as a subset sum. Now we still have a few remaining elements, and we'll group them in type 4. So for all of the uncolored elements, we can check easily that all of them have to be smaller than n over d. So the reason is that all of the elements that are at least n over d are already covered by the 2 color classes in step 3. So the remaining elements are less than n over d, and we can show that there are few of them. So we can just group them into size d color classes. And now we guarantee that each color class has sum smaller than n. So we also avoid n as a monochromatic subset sum. And okay, once we piece together all the 4 types of color classes, we can see that this is the number of colors that we need. Okay, any questions before I discuss the lower bound? Okay, so next I will discuss the lower bound. And first I will talk about Vu's argument for the bound that is n to the 1/3 over log n. And still, so Vu's argument used this results with Szemerédi and Vu, which shows that if we have a subset of the interval from 1 to n, and a subset has size at least a big constant times square root of n, then sigma of A will have to contain a long arithmetic progression, an arithmetic progression of length at least n. So how do we use this result? Let's consider an arbitrary R coloring of n, where we assume that R is sufficiently small, it's smaller than a little constant times n to the 1/3 over log n. In fact, we'll just focus our attention on this dyadic interval from n to the 2/3 to 2n to the 2/3. And in fact, only on the primes that are contained in this interval. So there are roughly n to the 2/3 over log n primes that are contained in this dyadic interval. And because we R color those primes, there will be a set Q of primes in this dyadic interval, which is contained in the same color class. And so we fix Q to be the most popular color class of primes in this interval. So we know that Q has to have size at least roughly n to the 2/3 over R times log n. And now if we plug in our choice of R, we can check that Q have size at least a big constant times n to the 1/3. So this is exactly the threshold where we can apply the theorem of Szemerédi and Vu with a square root the size of the interval, which is roughly n to the 2/3. So we'll split Q into two subsets, Q1 and Q2, let's say of equal size. So Q1 have size bigger than a large constant times n to the 1/3, and therefore by Szemerédi and Vu's theorem, sigma of Q1 contain an arithmetic progression of length at least 2 times n to the 2/3. And then now again, by using Graham's lemma, we can extend this initial interval of length roughly n to the 2/3 to one that is of much longer length. And we can check that after we extend this interval, the longer interval will be forced to contain n. So there will always, n can always be represented as a monochromatic sum. In fact, just a monochromatic sum using only the prime, the monochromatic prime in the dyadic interval from n to the 2/3 to 2 times n to the 2/3. So the key step here is the step where we apply Szemerédi and Vu's theorem, and that's also why the step that dictates the final value that we get. So in order to apply this theorem, we need to have that the set Q, or rather Q1, have to have size on the order of square root the size of the interval that we are considering. And in order to improve over Vu's bound of n to the 1/3 over log n, what we'll do is to try to improve Szemerédi and Vu's theorem. However, this result is tight in the sense that even if you just replace this big constant C by a little constant, by a small enough constant, then immediately we don't expect there to be a long arithmetic progression in sigma of A. The length of the longest arithmetic progression in sigma of A will significantly drop below n. And therefore, we must use some special property of A in order to improve over this result. And that is indeed our key new idea. And we show that once we know more about the additive structure of A, for instance, if we know that A is a set of primes or numbers that are close to being prime-like, then we can improve over Szemerédi and Vu's theorem. So this is a simplified version of a lemma that we use in the argument. And it roughly says that if A is a set of primes in this dyadic interval, and it has this size, so here gamma is roughly on the order of 1 over log n, so it's log n over log n, then if we know the extra condition that A is a set of primes, then we can show that sigma of A contains an interval of length 2 gamma times n to the 2/3. So the statement, the condition and the statement here is mostly similar to the theorem of Szemerédi and Vu, except that if we look carefully, the size of A that we need to assume here is gamma times n to the 1/3, and it is much smaller than square root of the size of the dyadic interval that contains A. So we are going below the threshold of square root n in the theorem of Szemerédi and Vu. And there we use this condition that A is a set of primes explicitly. So I'll give a very rough sketch of how we prove this type of lemma. So we'll use our general framework that proceeds in 4 steps. And as I have remarked before, the key step in the argument is the second step, where we want to show that sigma of A prime taken modulo M for some appropriate M and appropriate subset A prime of A is large. And again, as in the previous proof sketch, this can be reduced to the analysis of the set of almost periods. So we'll iteratively add elements to A prime, and we'll see how the set of subset sums modulo M grow. And to show that it grows by a large amount in every step, we'll control the set of almost periods in each step. And to control the set of almost periods, we have to, we'll use inverse results in additive combinatorics. So we use Feynman's 3.4 theorem, and also a version of the Selberg fifth. So this is where the condition that A is a set of primes comes in. And in fact, our argument is more complex because we cannot use just primes. Based on the divisibility structure or the prime divisors of N, we have to choose the elements that we use to consist of more than just primes. And then we have certain divisibility issues. So unlike the previous proof sketch, we cannot take the partition in the framework arbitrarily, and we have to use probabilistic arguments to handle divisibility issues. Okay, so we have also a generalization of our previous result. So if we let f of n and m to be the minimum number of colors R, so that if we color the positive integers less than n, we can avoid m as a monochromatic sum. So this just means that our previous f of n is simply f of n and n. But we don't have to fix the number that we avoid to be equal to n. We can choose it to be any number m in a reasonable range. So it's only interesting when m is at least n and it's at most n choose 2. And we also asymptotically determine f of n and m up to an absolute constant across the entire range of m. So this is how f of n and m grows. And the first term here, as you can see, is very similar to the terms that appear in our bound for f of n. So when m is smaller than n to the 3/2, the behavior is similar to when m is equal to n. But when m is large, is particular when it's bigger than n to the 3/2, the answer changes to a different form, and it's given by a different function rho n m that I will not define here. But it's a new function that starts to control the estimate when m is roughly n to the 3/2 up to n squared. Okay, so those are all that I want to discuss regarding monochromatic subset sum. Next, we'll turn to an extremal question. So it will also be about representing a given integer, but now our question will be about the extremum set A, so that the set of subset sum of A avoids a particular element m. So G and m is a maximum size of a subset of the interval from 1 to n, such that sigma of A doesn't contain a fixed element m. And so this was a previous question of Erdős and Graham. And Alon in 1987 determines the growth rate of G and m for m in this range from n to the 1 plus epsilon up to roughly n squared over log n squared. And he shows that it is on the order of n over s and d of m. Here, s and d of m is simply the smallest positive integer that is not a divisor of m. So we can see why this pops up very naturally. So if we choose our set A to contain of just all of the multiples of m, then all of the multiples of s and d of m, then certainly the set of subset sum will not be able to contain m. And therefore we have that G and m is at least n over s and d of m, roughly. So the point here is to show that there's an upper bound that's on that order. And then later, Alon and Feynman improved the bound to an exact determination of G and m, which is this number here for m sufficiently large. So for m bigger than n to the 5/3 roughly. And again, this one corresponds to a natural lower bound. So we can take all of the multiples of s and d of m, and then we can add in a few extra elements that are not multiple carefully so that we can avoid m. And so we can construct this as a natural lower bound. And they show that surprisingly, it is also the upper bound. for M in this range. And a result of Lipkin determines G and M up to 1 plus 0 of 1 for a certain range of M. And then Tran, Vu, and Wood in 2009 determines G and M across this entire range up to 1 plus 0 of 1. So we know that it matches with this function here up to 1 plus 0 of 1. And in our result, across the in roughly entire range, we show that for all M at least a big constant times n log n, and at most roughly n squared over 8 times log n squared, G and M is exactly equal to S and M. And when M is bigger than n squared over a constant times log n squared, then we determine up to 1 plus 0 of 1. So when M is very near to n squared, the answer switches to square root of 2m instead of S and M. So roughly we switch from a divisibility obstruction to a size obstruction. And the key ingredient behind this result is a strengthening of a previous result by Feynman and Sarkozy and Szemerédi and Vu. So we say that an arithmetic progression is homogeneous if every single term in the arithmetic progression is a multiple of the common difference D. And Feynman and Sarkozy proved that if A has size is a subset of n and has size at least square root times n log n, then sigma of A will have to contain a homogeneous progression of length at least n. And if you know, this is very similar to the theorem of Szemerédi and Vu that we stated earlier, except that this constraint is slightly stronger, and but the conclusion is also stronger in the sense that we obtain a homogeneous progression, not just a progression. And in fact, we show that in general, we can use the constraint in Szemerédi and Vu's theorem, so A is bigger than a constant times square root of n, and still obtain a homogeneous arithmetic progression. So this is the key tool in our exact determination of G and M. And in fact, this homogeneity is useful for several applications. So I'll just quickly discuss one application where it just directly improves the best known previous bound. So this is a question about non-averaging set. And we say that a set A is non-averaging if no element of A can be written as an average of other elements of the set A. So if you are familiar with Roth's theorem, then Roth's theorem can roughly be restated as the maximum size of a set A for which no element of A can be written as an average of two different elements in the set A. So here we drop the constraint on the number of elements that we can take the average over. And then we say that a set is non-averaging if no non-trivial average of elements of A is equal to one element of A. And previous results of Bosnay give a lower bound of roughly n to the 1/4 for the maximum size of a non-averaging set. And Erdős and Sarkozy, using the previous result of Sarkozy, shows that it grows at most by square root of n log n. And using our homogeneous strengthening of Szemerédi and Vu's theorem, we immediately improve this bound to a constant times square root of n. Okay, so in conclusion, we in this work we provide a general technique to show existence of long interval in a set of subset sums, and it can be applied to give tight bounds on several problems around subset sums. So if we first look at a class of problems around complete sequences, so these problems are about representing arbitrarily large positive integers as subset sums. And the second question, we look at the question of representing a fixed integer m as a monochromatic subset sum from some coloring of the interval from 1 to n minus 1. And then we also look at and then we use a technique to give a homogeneous common strengthening of previous results of Feynman and Sarkozy and the theorem of Szemerédi and Vu, and we use that to give an exact determination of an extremal function on the maximum size of a subset that avoids a fixed integer as a subset sum. And that also improves some previous bound, for example, on the size of on the maximum size of a non-averaging set. So that is all I have, and thank you for listening.